In today's video, we'll continue with Chapter 8. In this section, we'll be testing a claim about a proportion. Specifically, we'll be going through two examples that do the hypothesis testing method using the critical values. Our objective will be to conduct this formal hypothesis test for a claim about the population proportion P, but we'll need to define the other parameters and statistics that we'll be dealing with in this section. Here is a list of our notation. N will be the sample size or number of trials that are conducted. P is the population proportion. This is the one that we're using for the null and alternative hypotheses. P hat will be our sample proportion. It will be the proportion seen in the study or in the poll in our examples. And Q will be the population proportion complement, 1 minus P. Again, as with all things, there are some initial requirements, although for our cases, they will all be satisfied to simplify our work. Once we have our null and alternative hypotheses written, what we need to do is compute our test statistic. And again, for testing a claim about a proportion, our test statistic is a z distribution listed here, where z is equal to p hat, our sample proportion, minus p, our population proportion, all divided by the square root of pq divided by n. This is going to be the value that we will check whether or not it's in a critical region, depending on our value for alpha. So here's the example we will deal with. 1,009 consumers are asked if they're comfortable with having drones deliver purchases, and 54%, or 545 of them, responded no. And so with these results, we want to test the claim that most consumers are uncomfortable with drone deliveries. And again, we interpret most to mean more than half or greater than 0.5. So let's go through this example. Recall, our claim is that most are uncomfortable with drone deliveries. So that would be that P, our proportion, is greater than 0.5. And so what we want to do is we want to turn this into the opposite first. That would be P is less than or equal to 0.5. So our null hypothesis will be the case where our parameter P is equal to our value, and our alternative hypothesis will be which of these two does not contain the equality, and for us, that's the initial claim. So our alternative hypothesis will be P is greater than 0.5. We have our null and alternative hypothesis. This tells us right here that because we have a greater than sign, this will turn into a right-tailed test. What is not stated, but will be in every other example we have, is the alpha level, our significance level. And in this case, our significance level is going to be 0.05. And if we recall, what that means is when we have our normal distribution with a 0, our critical value, z, is going to be such that the area all the way to the right of this is my 0.05. And why do we know it's all the way to the right of it? It's because of our alternative hypothesis. Because it's greater than 0.5, we have a right-tailed test. All of our significance must be found in that tail. So the entire 0.05 must be contained to the right of our critical value z. And as we've called this before, this area here is our critical region, right? First thing we have to do is compute what z-score actually marks off that critical region. Again, it's going to be the z-score with an area to the right of 0.05. However, our z-table does not tell us areas to the right, it tells us areas to the left. And 0.05 is equivalent to having an area to the left of 0.9500. So what we have to do is look at our standard normal distribution table to find an area to the left of 0.9500. If we look at our standard normal table, we see that we don't exactly have a value of 0.9500, but values that are equidistant. We have something to the left and to the right, the same distance away from that 0.9500 we're looking for. And in that case, we want to find the mean of those two z-scores. Lucky for us, the table gives it to us automatically. that an area to the left of 0.9500 corresponds to the z-score of 1.645. That is not our test statistic, but that is the value that marks off the critical region. So we can put that down in our standard graph. Again, what that analysis told us was this z-score is 1.645. That will mark off the critical region when we compute our test statistic and use the critical values method to test the claim for this proportion. So let's compute our test statistic. If we recall, this was the formula for our test statistic. Our p hat was our proportion in our sample. That was 54%. So as a proportion, it's 0.54. The population proportion comes from the hypotheses. That's 0.5. That makes Q 1 minus 0.5, so it's also 0.5. And finally, N is that 1,009 people from our study. So we can compute this. The 0.45 minus 0.5, all divided by the square root of 0.5 times 0.5 divided by 1009, just like that. If I compute that, I'll get 2.55. And this is our test statistic value. So as we stated, our test statistic was 2.55. And what the critical value method does is it creates the critical region. We found that this critical value was z is equal to 1.645. That is the z-score that has an area to the left of 0.95, which gives us the area to the right of our alpha value. What we want to do is figure out, is this value, our test statistic we computed, inside of this green critical region? If it's marked off by 1.645, I know that 2.55 has got to fall somewhere to the right of that mark. It's got to fall somewhere into the critical region. So the test statistic is in the critical region R. And so what can we do with our conclusion? Because the test statistic was inside of the critical region, we reject the null hypothesis. We reject HO, and we can support the alternative hypothesis H1. That is how all of these questions will end. We'll either determine that our test statistic falls inside or outside the critical region. If it falls inside, we can reject the null hypothesis and be in support of the alternative hypothesis. If it falls outside of our critical region, then we fail to reject the null hypothesis and we cannot support the alternative hypothesis. Let's go through one more example. Here, we want to test the claim that fewer than 30% of adults have ever sleepwalked. So we're using sleepwalking data from over 19,000 individuals and a sample proportion of 29.2% to try and test that claim that fewer than 29 or 30% of adults have sleepwalked. What we were doing is we're going to use, again, a 0.05 significance level to test this claim. And so what we have to do, again, first is come up with our hypotheses, then determine the critical region. Third, find our test statistic. Fourth, determine whether the test statistic falls inside of our critical region. And lastly, whether that does or does not fall inside the critical region, we can reject or fail to reject the null hypothesis. So let's continue. So our claim is fewer than 30% of adults have sleepwalked. As symbols, this would be that P is less than 0.30. Right? What we want to do to determine our null and alternative hypothesis is we take our symbolic version of our claim, and we also want to look at the complete opposite version of this, which is P is greater than or equal to 0.30. Our null hypothesis is always the case where it's equal to our value, and our alternative hypothesis, again, comes from whichever of these two does not contain equality. And in that case, that would be P is less than 0.30. This tells us now, because it is less than a value, that we're going to have a left-tailed test, that all of our significance value of 0.05 is going to be all the way to the right, all the way to the left of our value, right? We can draw our standard normal curve, 0, because I have a left-tailed test that tells me I want a z-score where the value all the way to the left is my significance level alpha of 0.05. So what we can do is actually read the chart value that gives us a critical value of 0.05 to the left. But again, if we look at where we are on this number line, this is definitely going to be a negative z-score because we're to the left of 0. So let's take a look. Again, I'm looking for a z-score that gives us an area to the left of 0.05. And if I look right here, I notice I have two values that are equidistant from 0.05. And so I want to take their mean. But again, this is the case where this chart has done this for us, that a z-score with an area to the left of 0.05 is going to be negative 1.645. So that becomes our critical value on the chart previously. So the z-score is negative 1.645. That will mark off the critical region. Everything to the left of negative 1.645 is inside of this critical region. So determine whether we can whether we can reject or fail to reject the null hypothesis, we have to compute our test statistic in this example. Again, our test statistic formula for a proportion is z is equal to p hat minus p divided by the square root of pq over n. And so if we recall from the example, p hat was the proportion of people in the survey that slept walk. That was 0.292. The sample or the population proportion was 0.30. That comes from our claim. Q is 1 minus p, so this will be 0.70. And n, given earlier in the problem, was 19,136. So now we can compute this. Z is equal to 0.292 minus 0.30, all divided by the square root of 0.3 times 0.7, all divided by 19,136. If I compute this, I get negative 2.41 as my test statistic. So let's check whether that is in or is not in the critical region. If we recall from above, here is our standard normal graph with the critical value of negative 1.645 that corresponds with the left-tailed test of having the significance level alpha being 0.05. And we just computed our test statistic z to be negative 2.41. And so what we want to do is determine whether negative 2.41 is in our critical region or not. As we can see, the values here fall between 0 and our critical value, negative 1.645. That means negative 2.41 is going to be somewhere to the left of that critical value, which means it falls inside the critical region. So our conclusion, right, because our test statistic is inside the critical region, we can reject the null hypothesis, H sub 0, and support the alternative hypothesis, support H1. Hopefully this was helpful. If you have any questions, send me an email. We can set up a Zoom office hour. Have a good day.